We ended off last time's discussion on alcohols by mentioning that alcohols were amphoteric, which is a word you'll have learned in Gen Chem. Amphoteric species are those that can act as either an acid or a base. And examples of amphoteric species include water, include ammonia for certain, NH3, and also include alcohols. So last time we talked about how it is that alcohols can act as acids. We said that if you take an alcohol such as methanol, and here I'm using methanol just as an example, I could have picked any other alcohol, and you treat it with a really strong base such as the conjugate base of ammonia, which is NH2 minus, very, very strong base, and it requires a very strong base to deprotonate an alcohol. But you will then get the conjugate base of the alcohol, which is in this case the methoxide ion, and you'll get ammonia as the other product. And the way you can tell this reaction is going to proceed in this direction is by having at least some rough idea of the pKa's of the acids. And so methanol is going to have a pKa round in about 16. If you know that it's in the mid to high teens, I think that will be close enough. The pKa of ammonia is considerably higher. I should have it memorized, but I don't. I think it's somewhere in the 30s, mid to high 30s. So remember that the reaction, this is also something you'll have covered in Gen Chem. The reaction should always favor, not should, will always favor formation of the weaker acid. And remember, the one with the higher pKa is going to be the weaker acid. And that makes sense because the weaker acid is going to be the one that less wants to be without its protons. So the species would much rather be NH3 than NH2 minus as compared to methanol and CH3O minus. So there's an example of an alcohol acting as an acid. I really should have put that up here, acting as acid. And what about an example of an alcohol acting as a base? Well, we could take our methanol again. And again, I'm just using methanol as an example. I could have picked any other alcohol. And you treat it with a really strong acid, something like sulfuric acid. Well, you'll get, let me even put in my lone pairs just for clarity. You'll get the conjugate acid of methanol and the conjugate base of sulfuric acid, which is the bisulfate ion. And so what's happened here is sulfuric acid, of course, being a very strong acid, has done its duty as an acid and given up a proton, given up H+. And when you take away H+ from H2SO4, you get HSO4 minus. You get the conjugate base. And it's donated that proton to methanol. Methanol is able to act as a base also, just like any other alcohol can, by virtue of these lone pairs that it has on its oxygen. Those can be protonated. And you will get the conjugate acid of methanol, which would look like that, and now it would have a plus charge. And you can verify for yourself that both of these equations are balanced. Remember that when we balance equations, we balance not only for mass, but also for charge. So for example, in the first equation we had over here, the total charge on the reagent side is -1. You have 0 and -1. And the total charge on the product side is also -1. You have -1 plus 0. And likewise down here, the total charge on the reactant side is 0. The total charge on the product side is also 0. You have +1 and -1. Those cancel each other out, and you have a total charge of 0. So that's something that we often forget when balancing equations. We understand they need to be balanced for mass, but they must also be balanced for charge. The total charge on both sides of the equation must be the same. So all this is to say that this is just to give some examples to illustrate that alcohols are amphoteric, that they can act as either acids or bases. And that's not surprising because alcohols are in many ways very similar to water. We said that alcohols are one of the organic derivatives of water. All we've done is taken a water molecule and replaced one of the hydrogens in water with an alkyl group. So it's no wonder that they exhibit some similar behavior. Water is amphoteric, so alcohols are also amphoteric. Let me just make sure I'm not missing anything. I have some information in your class notes about phenol. Remember, phenol is hydroxybenzene. You learned what phenol was called actually in chapter 4. So this is review from chapter 4. And we said that phenol is an alcohol, but it's a special alcohol. Phenol is much more acidic by something like 100,000 or 1,000,000 times more acidic than aliphatic alcohols like methanol and ethanol and butanol. So that's going to affect the properties of phenol in comparison to aliphatic alcohols. And we introduced that term aliphatic alcohols the last time. Those are alcohols with an alkyl group like methyl or ethyl or butyl. And so phenol, your book points out that phenol can act as a base, and that is true, but it's much less good at acting as a base than methanol or ethanol or butanol would be. Since it's a stronger acid, it would make sense that it's also a weaker base. So I mentioned that in the class notes. I just thought that needed some clarification. Your book is right. It's just not nearly as good a base as something like ethanol or butanol. And that, I think, is going to affect what we talk about later in some of the other reactions that involve alcohols, particularly when we talk about making esters, which is going to come up in, it might be chapter 10 or 11. We'll get to it eventually. But we'll learn there that it's very easy to make, let's say, a methyl ester using a process called Fischer esterification. Making phenyl esters is much more difficult. There are ways to do it, but you have to use far more reactive compounds in order to get that done. By the way, speaking of alcohols, I just happened to notice this big thing of alcohol wipes and was rather surprised that it uses ethyl alcohol rather than isopropyl alcohol. Isopropyl alcohol is rubbing alcohol, and you can, of course, go to the store and buy that. Isopropanol is toxic. You don't want to drink that. Ethyl alcohol, as you're aware, is equally good at killing germs. However, even without looking at it, I can guarantee you that any alcohol that's on these wipes is going to be what's called denatured, which means they add things to it to make it undrinkable. So do not drink denatured alcohol. It is toxic. They add things like methanol and ethyl acetate and other toxic compounds like that to render it undrinkable. So just a little public service announcement. Do not drink denatured alcohol. It's very toxic and bad for you. They purposely add things to the alcohol, even though ethanol is the intoxicating component in adult beverages. Though ethanol is only very slightly toxic. You don't want to drink too much of that either for obvious reasons. But denatured alcohol is quite toxic. So do not drink denatured alcohol. You will regret it. Good. So much for that, I suppose. Let's move on to dehydration of alcohols. We're talking here about the reactions that alcohols can undergo. And one reaction that alcohols can undergo that I want to focus some time on today is dehydration of alcohols. And dehydration is exactly what it sounds like. It means loss of water. And the product is going to be an alkene. This is essentially going to be the opposite of the reactions of the type we learned in chapter 3. So I want to spend a little time talking about dehydration. I then want to talk about the reaction of alcohols with hydrogen halides also. And we'll just get started on the oxidation of alcohols. I won't go fully into it. We'll just get the topic started. But there is, I should maybe make a change to the class notes. The first few sentences in the class notes portion, in the 7.8 portion of the class notes, which is actually what I'm referencing right now, has a few sentences at the beginning that makes references to chapter 6, which of course we did not do and you are not responsible for. You still might want to glance at those sentences at least, but of course, that's one of the chapters that I dropped is chapter 6. So you guys are not responsible for chapter 6. But we don't need chapter 6 to understand dehydration of alcohols. And the nature of the reaction is that if you take an alcohol with at least one hydrogen on the carbon next door to the alcohol, we call that the alpha carbon. We use Greek letters. Alpha means next to. So there's the actual carbon with the alcohol on it, and then there's the carbon alpha to it. And you do need at least one hydrogen alpha to the OH group in order for this to work. And in general, we treat this with some strong acid. Sulfuric acid is pretty typical. There are others you can use. You can use phosphoric acid, for example, but sulfuric acid would certainly work just fine. And what you will get is the corresponding alkene. By corresponding, I mean that it has the same number of carbons, and you will also get a molecule of water. If we were being picky and balancing the equation for mass, we would want to mention that a water molecule also does get generated. So for example, if we were to take actually, I'm going to use an easier example than is in my class notes. If we were to take cyclohexanol and treat it with sulfuric acid, we would get cyclohexene. So we'll remove, there's 4 hydrogens next door to the carbon bearing the alcohol functional group. All 4 of those hydrogens are the same. It doesn't matter which we take off. The product is going to be cyclohexene. And yes, you will, of course, get water as well. Especially be careful on OWL, because sometimes they want you to mention inorganic side products in a separate sketcher. Sometimes they don't. So read the directions carefully. I normally focus on the major organic product, just because as organic chemists, we're mostly focusing on the organic species. We're much less concerned about inorganic species. To give a slightly different example, let's say that we took 1-methyl cyclohexanol. We treated this with sulfuric acid. The major organic product would be 1-methyl cyclohexene. And you can see in both cases, we've removed the OH, we've removed a hydrogen next door to that carbon that has the OH group, and we've put a double bond where put in a double bond so as to make all the carbons obey the octet rule. So I've included that in the class notes also. I've given you a step-by-step method for how to find what the structure of the product is. Step 1, remove in no particular order, remove the OH. Step 2, remove a hydrogen on the carbon next to the OH group. And step 3, put a double bond in so as to make all of the carbons obey the octet rule. So all that is there in the class notes. Just to give another example, in the class notes, I mentioned 1-propanol. There's 1-propanol. If we dehydrate 1-propanol using sulfuric acid, or again, some other strong acid, we will get propene plus water. So again, you can see what I did. I took away the OH group. I took away a hydrogen next door to the OH group, and I put in a double bond so that those carbons still obey the octet rule. But you can see that pretty soon it becomes evidence that we have, or it becomes evident that we have an issue with all of this, which is, what if not all of the hydrogens next door to the OH group are equivalent? What if it makes a difference which hydrogen you pull off? So the answer is that you get the more substituted alkene, which means you will get the alkene that has more alkyl groups directly attached and fewer hydrogens directly attached to the alkene carbons. And as an example, let's say we took 2-methyl-2-pentanol, which would look like this, 2-methyl-2-pentanol. The name is in the class notes. Well, we have a problem. Are we going to take off this hydrogen? Or if we took a hydrogen off that methyl group, those are the same. The 2 methyl groups are equivalent. Or are we going to take off one of these hydrogens? Which do we take off? And the answer is we take off whichever one will give us a more substituted alkene, which turns out to be that one. So if we treat 2-methyl-2-pentanol with sulfuric acid, we're going to take off one of those hydrogens. And so the product we get will look like this. So let me put some colors in here to give you some visual aids. We're going to remove the hydrogen from that carbon. We're going to remove the OH group, and we're going to form a double bond where I've circled in red. So as opposed to taking off one of these 6 hydrogens, that will give you the same compound. So you will get that compound and not that compound. In other words, you'll remove one of the H's on this interior carbon. The reason is you get a more substituted alkene. This alkene has 1, 2, 3 alkyl groups attached directly to the alkene. This alkene has only 2 alkyl groups and 2 hydrogens. This one has 3 alkyl groups and only 1 hydrogen. Again, let me circle the alkyl groups so you see what I mean. There's 1, 2, 3 alkyl groups directly attached to the 2 alkene carbons. This one has only 2 alkyl groups directly attached to the 2 alkene carbons, 2 alkyl groups and 2 hydrogens. This one has 3 alkyl groups and only 1 hydrogen attached to the 2 alkene carbons. So that's going to be where we form the double bond. And that's with no exception. And actually, I gave an example up here, almost without realizing it. In this case, the alkene you get is this one over here and not that one. That alkene is less substituted than this alkene. So again, maybe let me actually draw in the H's in question. There's this one and there's that one. So the one that we're going to remove actually is this hydrogen. And we're going to form a double bond between those 2 carbons, not between those 2 carbons. So we'll remove this hydrogen and not that one. The reason is that in the end, we will get an alkene with 3 alkyl groups directly attached to the alkene. On this one, you have only 2 alkyl groups directly attached to the alkene. So you want the one with more alkyl groups directly attached to the alkene. So if you're in a situation like this and you're wondering, let me answer your question first. Well, the question is, do you want to choose the hydrogen that's interior? You can say it that way. It's just, I don't know always how obvious that's going to be, which is more interior. It might depend on how the structure looks. So you're right. The answer to your question is yes. But what I would say, what I was just about to say was, if you're in a situation and you don't know which to pick, draw both. And then you pick the one that has the more substituted alkene. The alkene that has more alkyl groups and fewer hydrogens directly attached to the alkene carbon. So I hope that answers your question. I think the answer to your question is yes, but I'm saying, and I don't mean just you, of course, I mean all of you. If you're in a situation where you don't know which to pick, draw both of them. And then you can pick whichever one is the more substituted alkene. I think you'll find there's always one that's more substituted. So, so much for dehydration of alcohols. Boy, we might end very early indeed. I don't suppose there are any objections if that's the case. Any other questions on dehydration of alcohols? I can do another example if you'd like. Oh, did I hear yes? Oh, sure. Sure, absolutely. Let's see. Fortunately, I've kind of exhausted all of the possibilities. Well, I might be, ooh, that's blue. I want black. Well, this will work. Sure, that one will work. So the question is, will we take off this hydrogen or the other hydrogen, the one over here? I've actually already given maybe I'll do it the other way. Let's say you don't know which to take, so draw both of them. Let's try that method. Because it'll only just take you a few more seconds to draw both possibilities. So one possibility comes from taking off this hydrogen. the one on the left. So we take off that hydrogen in the OH, and we will get something that looks like this. The other one comes from taking off the hydrogen on the right in the OH group. And let's say we don't know, so we're just drawing them both out just to see. I think then you will get that alkene. And so now you can see this alkene has just one alkyl group directly attached to the two alkene carbons. This one has three alkyl groups. So that's the one we're going to pick, not this one. So maybe that's an even better way to do it. Let's say just draw them both, and whichever alkene is more substituted, that will be the major product. Maybe that's an even clearer way to do it. Sure, is that kind of what you meant? Yeah, just wanted to make sure. Good, any other questions then? Oh, that's a good question. If there are two OH groups, would you take both of them off? I would guess so, yes. I think eventually you would eliminate both. Now, I'm also not going to ask you something that you literally cannot tell what the answer is. Any questions in my exams will be fair, at least ones that I believe to be fair. Of the sulfuric acid, if you have an excess of the sulfuric acid, which you will. I'm trying to, let me see if I can think of one that gives only one product. While I'm erasing, I'll think. Do you need more H's or fewer H's? You need fewer H's, more alkyl groups directly attached to the alkene carbons. So look at where the alkene is and count the alkyl group. You can do it either way. You can either count the hydrogens that are directly attached or the alkyl groups that are directly attached. And you want more alkyl groups and fewer hydrogens. So you can do it either way. Both will work. So you see over here, this one has just one hydrogen and three alkyl groups attached. So that's the one we'll pick. The other one is only one alkyl group and three hydrogens attached. So you'll get the same answer either way. It doesn't matter which way you do it. Oops. Not that it really matters a huge deal, but looks funny. So maybe I'm here, this is what you asked about. I'm here making up a question that I would consider fair for the exam. I'm trying to make it so there's only one possible answer. If you treated this with sulfuric acid, then I guess that you would get cyclopentadiene. I think you'd take, well, you could draw it several different ways, but I think that's what you would get. And that one's nice because there's only one possibility. You're not going to have the two double bonds accumulated, not in a ring like that. Couldn't fit. But yes, would that happen? I think that would. Yep. Good questions. Other questions then? All right then, let me move chat back over. Chat is not very chatty today, which is okay. They don't have to be. It's not required. Good. So the next reaction of alcohols, and again, I think it makes sense in a chapter on alcohols to talk about what alcohols do, right? To talk about what types of reactions they undergo. So they can undergo dehydration. We just had that one. Alcohols can also react with with hydrogen halides. Can I go RXN for reaction of alcohols with hydrogen halides? And by hydrogen halides, I mean either HCl, HBr, or HI. Any one of those would work. I won't say hydrogen fluoride is not a hydrogen halide, it is. But again, remember the hydrogen fluorine bond is extremely strong. Very, very difficult to break that bond. So HF will not work in this type of reaction. You want only those that are strong acids. And I think you learned in Gen Chem, HCl, HBr, and HI are strong acids, whereas HF is a weak acid, again, because of that strong hydrogen fluorine bond. So these are the only ones we can use, but any one of those three will work. And the idea is, just in terms of a general case, if you have an alcohol, and I should say the alcohol can't be phenol, that will not work. This will not work for phenol or substituted phenols. But you can treat it with HX, where X is chlorine, bromine, or iodine. And you will get the corresponding alkyl halide. Again, by corresponding, I mean it is the same number of carbons. And you will also get a molecule of water. You can see that's going to happen. We take the H from the hydrogen halide and the OH from the alcohol, and we will get a molecule of water. So the major organic product will be the corresponding alkyl halide. And it'll be either a chloride, a bromide, or an iodide, depending on which hydrogen halide you used. So for instance, if we used 1-butanol and treated this with, let's say, HBr, you would get 1-bromobutane plus water. Again, for my money, I don't really care if you mention the water or not. But read the directions on OWL carefully, because sometimes they care and sometimes they don't. They may literally want you to put in a separate sketcher and put a water molecule in it. So read the directions carefully. Likewise, if one took 1-methylcyclohexanol, which we had before in one of our examples, and let's say we treated that with HCl, you would get 1-chloro-1-methylcyclohexane plus H2O. And now I'm trying to remember what was the other, just want to be sure I do all the same examples. We had one that looked something like this. I think I would anticipate, at least for our purposes, if we treated this with HI, you would get the corresponding iodide. Actually, no one hears me saying this. That's a lie. It would undergo a rearrangement. But for our purposes, that's the answer I would expect you to put. Just look where the OH is and replace it with whatever halogen is in the hydrogen halide you're given. That's close enough for our purposes. I don't want to burden you with too much beyond that. And that then gets back to your question about what if there's multiple ones? Well, I would expect they would all. They would all get changed into halides. So if we treated this, let's say, with HCl, again, exactly like you said, assuming there's an excess, which I think there would be, you would expect to get the dichloride, 1,3-dichlorocyclopentane. At least that's what I would expect to happen. Good. Yeah, only aliphatic alcohols. And I mentioned about phenol on the next page of your class notes. So this only works for aliphatic alcohols, meaning alcohols with an alkyl group attached to the OH group. But other than that, it's quite general. You can convert alcohols to hydrogen halides very readily this way. There are other ways besides, but this is a pretty common way to do it. And the nice thing about this reaction is, I think I said something like over half or nearly half of all syntheses start with an alcohol as the starting material. I wouldn't be surprised if most of the remainder started with an alkyl halide. So this is a way to convert an alcohol to an alkyl halide. So this gets used a lot in the chemical industries, in the pharmaceutical industries, in anything that involves organic synthesis. Alkyl halides and alcohols are both really, really common starting materials. Good. So I think with that, I just want to get us started on oxidation of alcohols. And the idea behind this type of reaction is that we're going to take an alcohol and we need to have at least one hydrogen on the carbon that bears the OH group. And we're going to treat that alcohol with some oxidizing agent. And we'll talk about what those oxidizing agents are in a moment. So we'll just say parenthetically, O in square brackets means oxidizing agent. And by the way, is there a similar shorthand for reducing agent? There is. That would be H in square brackets. Just being very generic. We'll specify what the oxidizing agents are on Monday when we get back to this. But I just want to say in general that if you treat an alcohol of that type with an oxidizing agent, you will wind up converting the alcohol to a carbonyl compound, probably a ketone or aldehyde. And you also, the hydrogen winds up effectively in a molecule of H2. So, and again, I do need to stress, you do need at least one hydrogen on the same carbon as the OH group. If there is not at least one hydrogen, then no oxidation is possible. So for example, tertiary alcohols, which we already defined tertiary alcohols the last time. Tertiary alcohols are compounds of this type. You can treat them with any oxidizing agent you want. Make it as strong as you like. It doesn't matter, no reaction. So tertiary alcohols cannot be oxidized. And that's really all I wanted to mention today. We'll get into secondary and primary alcohols on Monday. I'm a little bit embarrassed ending a whole 15 minutes early, but I think it's, well, certainly we'll answer any questions. Yes. You need one hydrogen, at least one hydrogen, but unlike before, the question was about how many hydrogens we needed. Unlike, you may remember before, we needed the hydrogen to be next door to the OH group. Here we need it to be on the same carbon as the OH, and you need at least one. More than that is fine, but you do need at least one hydrogen on that carbon. Otherwise, the alcohol cannot be oxidized. Another way of saying the same thing is tertiary alcohols cannot be oxidized. You can hit it with the strongest oxidizing agent in the world and nothing will happen. Tertiary alcohols can't be oxidized. Good. Any other questions then? Well, I'm a little bit embarrassed, but it is Friday and I think we're all tired, so we might as well end it there. But we'll continue on here. On Monday, I'm also expecting I'll start chapter 9. If there's any extra time like this, I'll make up some review questions or something like that. And same thing on Wednesday. If we end early after doing some of chapter 9, we'll do some review for the exam. Good. Have a great weekend. We will see you then. Oh, good. I thought I had forgotten to record. Oh, you must be the person who emailed me about your water bottle. Yes, you found it. Good.